Yeah, today's lecture is the introduction to Euclidean geometry. And we always want to know, how do we know something is true? I mean, how can we prove something is true? I mean, someone could say that something is true, but how do we know that? And we know that nowadays there's very hard to find someone that we can trust. We cannot trust the media. We cannot trust our teachers. We cannot trust uh, our pastors. We cannot, definitely not our politicians. So, so that created such a big problem. And especially now we have this self media and social media. So there's a lot of things, um, you know, out there. They offer not just offer a different point of view, but also there is a lot of misinformation out there, and there are a lot of people who basically purposely lie and just to for some financial gain. Um, so I mean, uh, I think uh, most of you probably heard of the Ponzi scheme. Ponzi scheme basically is to use later people to pay people get in first, right? But eventually the whole system will collapse. But how do you know that something is not Ponzi scheme? And so this is actually the problem since the very beginning of the human civilization. And amazingly, that there is something happened in ancient Greek, and there is someone who came up with a system um, that help us to rationally figure out something is true. So when we're trying to figure out something is true, there are basically two kinds of reasoning, logic reasoning. One is called deductive reasoning, one is called inductive reasoning. And Euclidean, um, he wrote a book. It's called The Elements. There are 13 volumes of that book. And in that book, he showed us a way to do how to do deductive reasoning. So I'm going to give you an example of uh, what's the difference about the inductive reasoning and deductive reasoning. Now, inductive reasoning is something we do. Not us, we humans can do it, animals can do it too. And so the deductive, inductive reasoning is basically to, you see what's going on around you, and you're going to um, observe as much as you can. And then based on those examples, you came up with a general statement. And sometimes it's true, sometimes it's not true. So for example, why the ancient people think the earth is flat? Well, they used inductive reasoning. Uh, for example, if we look at the floor we have there, and I'll say our floor is flat, and we look at our neighborhood, which is roughly flat. I mean, there is some up and down, but roughly flat. And I live in Indiana, south of Indianapolis. So if you drive to Chicago, you have to use I-65, and you will see that on your way to Chicago, and you'll see everywhere is flat. So then we can come up with a generalization or come to a conclusion that Earth is flat. But that conclusion could be true, could be false. So the only way we know this is not true is that when we get to the ocean, we start to see the horizon actually is a little bit curved. And actually, the ancient Greeks realized that Earth was not flat, because when they saw boats uh, sailing towards them, they first saw the tip of the boat, and eventually you see the body of the boat or a ship. The tip of the ship, then eventually you see the body of the ship. And today, of course, if we go fly, get on an airplane, we see you'll see that actually don't, as long as you get to the ocean, you'll notice that the horizon is curved. So we know that, of course, now we know it's for sure it's not, Earth is not flat, because we have, we have airplanes, we have satellites, we have all kinds of things. But of course, you can still argue Earth is flat, but most of us will come to the logic conclusion that the Earth is not flat. As a matter of fact, the Earth is round. So this kind of reasoning, we do that all the time. And most sciences, like the physics and chemistry, they use this type of reasoning. So that's why they do experiment, they observe, they collect data, and from the data, they're trying to make sense out of it. But the things about inductive reasoning is that you can never be sure that you are right. So for inductive reasoning, you can prove something is not true, but you can never prove something is true. And so then with inductive reasoning, a lot of times we have to take it by faith. Now, for example, we see sunrise every day, right? We see that they came up yesterday, the day before yesterday, then we can come to a conclusion that the sun will rise every day. And that's pretty much what we count on every day. The sun will rise, which has been true until now. Of course, the science tells us that someday that our whole solar system will collapse. So eventually, we won't get there, but eventually the sun won't rise. All right. Now, what is deductive reasoning? Deductive reasoning is based on something we believe is true. Then from there, we go find a conclusion about any particular situation. So we have a general belief, believe that, for example, if we believe that the Earth is round, then the logical conclusion is if you're sailing towards one direction, you will eventually come back. And that's the faith that Columbus had, that for him actually to sail to America, because he believed that the Earth is round. And of course, eventually, he was proven right, except that he didn't really, he was trying to get to India, but he didn't get there. He got to America. For deductive reasoning, that we rarely use that. Most people have difficulty or unable actually to use deductive reasoning. It's because they never really know how, which is unfortunate, because when we learn in mathematics, and that's the purpose for learning mathematics, is that we can learn deductive reasoning. But that was not happening right now in America's education system, and not only in America, in most countries in the world. They just teach you how to do computation. But nowadays we have computers. We don't have to become human computers. You can learn all kinds of computation that you won't be able to hire, because we just cannot do better than computer. We are actually far worse than just even a simple smartphone. Okay. And for deductive reasoning, it's something that we can prove something is true based on our premises. So as long as our premises are true, then we can come to a logical conclusion. Okay. And this actually is a famous painting. This actually, the painting now is in the official residence of the Pope, and it was painted by Raphael, and I think in the 16th centuries, and that shows the ancient Greek um, it, the philosophers, and the one in the middle is with the hands pointing up. That's Plato, and so it's supposed to be his school, um, Plato's school. You see a lot of mathematicians, philosophers, and all that. And there is also one important figure here is this here, the one in the middle, and bent down and using a compass to draw some circle. That is Euclid. Okay, and we see that the Plato's Academy, and it was said that on the door of his academy, um, we have this inscriptions. It said that let no one unversed in geometry enter here. So basically, Plato, uh, we could say that he's the father of philosopher, Western philosophies. And so basically saying that if you don't know geometry, I mean, you forget about it. You cannot even talk about philosophy. And because learning geometry help us to master logic reasoning, and with that we are able to really talk about philosophy. And unfortunately, we don't have that requirement nowadays. In the past, if you go to college, you have to learn Euclidean geometry, and there is a very, very good reason for that. Because once you learn how to uh, think logically, learn how to use deductive reasoning, you will be able to figure out what is true, what is wrong, just on your own. You don't have to follow someone else. Okay, so now we get onto Euclidean geometry. Now, in Euclidean geometry, and you see the picture of Euclid here, and on the other side is the come from archaeological discovery. They find the part of his book here. You can see there is some kind of drawing there. So Euclidean geometry, the name is the elements. We talk about there are 13 volumes of the elements. So its importance you cannot overstate it. It is instrumental in the development of logic and modern sciences. So the reason now we have, I mean, we see a lot of technological advancement. We have computers and cell phones and television, and we can send a rocket to the outer space. All of that, physics, chemistry, and all of that, without Euclidean elements, um, it is impossible to have what we have today. Okay, and since the invention of the printing press and the Euclidean element, it was estimated that to be second only to the Bible in the number of editions, like how many times it was printed from a different master copy. And you can see that was so important, especially in the West. And not that long ago, about 100 years ago, I mean, if you want to be a scholar, you have to understand Euclidean geometry. So the amazing thing about Euclidean geometry that it started with 10 axioms. So 10 axiom means something that we take, we believe it is true. So we don't have to prove it, and that everybody can accept. And once you have that, then you can have something called propositions, which is a true statement that saying, I can do this, and this is true. And those things have to be proven. And once they are proven, then they are called theorems. So with just 10 axioms, and Euclides, in his book, Elements, has collected 465 theorems. And those theorems are very, very important. And the things about deductive reasoning, as long as your axioms are true, and you can, everything that was proven, you are sure they are true. So the only thing to disprove any theorems in his book is that one or at least one axiom is not true. Okay, so far, as far as geometry and two-dimensional and three-dimensional geometry are concerned, that all those axioms are, we cannot disprove them. We still hold them, they are true. And so therefore, 465 theorems are still true. So it's kind of amazing. Like in science, we know physics, chemistry, we always have new discoveries, and every time we have new discoveries, something we have to change. We have to change theory. But Euclidean's geometry, all his theorems are still never changed. They are still true. Okay, so let's look at those 10 axioms. The first 5 actually called common notion. Common notion means it's not just applied to geometry, it's applied any branch of math. So the first one is, say, things which equal the same thing also equal one another. And for example, if you have the same height, or let's see, here's you, and if you have the same height with a friend, like say this friend, and you have another friend, so this is your friend A and your friend B. Now, if you and your friend A the same height and your friend B have same height as friend A, then you know you and your friend B have the same height. You don't even have to measure it. So that's what it means. Things which equal to the same thing, in this case, this is a common thing, you and your friends have the same height with, then you and your friends must have the same height. You must equal. So the second one is, say, if equal added to equal, then the whole are equal. And this actually we pretty much take for granted now. It's like, say, if A is equal to B, then A plus C equal to B plus C. And that's the basics actually for algebra. So if you have two things, let's say 4 equal to 4, if you add exactly the same thing on both sides, now the end result definitely will equal to each other. And those things we basically take for granted. We in a way, we kind of, we don't have to prove it. We kind of like, we hold this as self-evident, just kind of in the Declaration of Independence. So something is true, we all agreed on. And number 3 is if equals are subtract from equals, then the remainders are equal. Okay, so same, that's basically come down from here. Say 4 is equal to 4. If you minus the same thing, the end result will still be equal. And this is one of the things we also take for granted in mathematics. And number 4 tells us, what do we mean by equal? They said things which coincide with one another equal one another. So that means if you have line segment and there's another line segment, if you can put line A on top of line B and they match, that means that both ends they match, then we say A is equal to B. So that's what we mean by equality. So to give us those so far we mean nowadays we take for granted. I mean that we just know if you say this is this, nobody going to challenge you. Number 5 said the whole is greater than any of its part. So which means say 7 is 4 plus 3, and so 7 is the whole, 4 and 3 are the parts. So therefore 7 is bigger than 4, 7 also bigger than 3. Now, the reason for that is back at that time, in Euclidean time, there's no concept of 0. So anything has to be bigger than 0. So if you have something like, say, 8 is, if you do 8 equals 0 plus 8, then we say the whole actually equal to this part. But they don't have the concept of 0. So everything is bigger than 0. So therefore, the whole is definitely greater than any of its parts. So those are called 5 common notions. And then we also have 5 postulate. So postulate, we're talking about the axioms that apply to geometry. So the first one is, you can see that pretty simple. You say that if you have 2 points, we can only draw one straight line. Now, of course, we can draw those on straight lines. We can have different kinds of that. So in Euclidean geometry, a line could be like that. So that's why it says straight line. So if a line like this, of course, we can have many different lines go through 2 points, but we're talking about straight line. So only just one. And second one is when we have a line segment or straight line segment, which is definite, finite, and we can extend that to both directions infinitely. So we'll just keep going. Okay, now we have that. And number 3, talking about circle, you said that we can draw a circle at any point at the center and any given segment as the radius. So if you have a compass, you can draw all kinds of circles. You can draw at any point as your center, and you can have any given segment. Of course, we're talking about ideal compass. Now, any practical compass, there is a limitation. There is, they're just, you cannot go indefinitely long unless you have a compass which is as big. I mean, even as big as Earth, you can still cannot do anything beyond that. So this actually is talking about the ideal compass. Number 4, all right angles are equal. So right angles, not something we take for granted. So right angles are 90 degrees, of course they're equal, but you have to, that's part of our belief. So we take that for granted. That means that's something we take it as the truth. We don't have to prove it. Nobody's going to challenge you if you say all right angles are equal. And this number 5 is very interesting. Number 5 said that if you have two straight lines and you put something cut through that, that's called transversal, cut through these two lines. If you add this angle and that angle, if the sum is less than two right angles means a straight angle, 180 degrees. If these two add together less than 180 degrees, then they're going to meet on this side. So they're going to eventually going to meet. Or if you line like this, now this side that bigger than 180, so they are not going to meet. But on this side, it's less than 180, so we're going to meet on this side. So the side that the angles, the sum of two angles are less than 180, they're going to meet. And so that's all we have. Just like we have a foundation now. We got 10 axioms, 5 are common notion, and 5 are postulate. And with that, Euclidean shown that you can build theorems on top of that. And like we said earlier on, there are altogether is 465 theorems. So this is a marvelous, this is an amazing, how to say that? It's amazing human, because they discover, or could say invention, but that's human was able actually to come up with that fact. It's just amazing. Okay, and I think you'll appreciate after you actually have learned the Euclidean geometry, or maybe as you are learning Euclidean geometry, you become more and more appreciative. Okay, so that's that. That's how we got started. And the tool, like we said that early on, we got compass, we got a straight edge, and here actually is the ruler. The straight edge has no markers, so you just cannot use that to measure. And the compass in the nowadays, the compass we can it will stay put if you lift the compass. But in the Euclidean's time, if you take the compass off the paper, then the two legs will collapse. So you cannot use the ruler to measure a line segment so that you can copy it, and you cannot using the compass actually to do to copy a line segment. So this is what we have for today, and the next lecture I'll talk about proposition 1. So then you have a taste of the Euclidean geometry.